This set of notes is going to take you through calculations involving Dalton's law of partial pressures and mole fractions. Dalton's law of partial pressures, one of the things that's new about this is that up until this point, we've been dealing with pure gaseous mixtures, which means gases that are composed entirely of one element or one compound. But in the real world, our experiments often involve mixtures of gases, meaning air, which is made up of many different types of gases. As you can see up here, this is the composition of air. And those gases are unreactive, so the total pressure of the mixture is then the sum of all the pressures of the individual gases. So each gas is causing a specific amount of pressure, and if you total each of those individual pressures, you get the total pressure that the entire gas mixture exerts on its container. So the Dalton's law of partial pressures tells us that the total pressure is equal to the sum of the individual pressure of all of the gases in that container. Mole fractions, we're going to get into a little bit later in this video, but mole fractions tell us the ratio of the number of moles of one component to the total moles of all components that are present in the container. But again, we'll get into that in more detail later. We're going to focus on the partial pressures law right now. So this is just an illustration to show you how Dalton's law of partial pressures works. So on the right-hand side, we have two gases. We have gas A with 1 atmosphere of pressure and gas B with 3 atmospheres of pressure. When I add those two together, 1 and 3 gives me 4 atmospheres of pressure. So the total amount of pressure caused by each of those individual gases, when I put them into the same container that is the same size, the pressures will add onto one another. So it is an additive amount of pressure. And then you end up with a total pressure of 4 atmospheres, the sum of both of those gases. So these problems are actually relatively easy. The most difficult thing about them is making sure that all of your units are matching, because we can't add things together if they don't have the same units. So the first thing you want to do when you're looking at these problems is check out your units. This one tells us a mixture of neon, argon, and xenon has a total pressure of 1,525 torr is the first unit. Then the pressure of neon is in atmospheres, and the pressure of argon is also in atmospheres. And it asks us for the partial pressure of xenon in the mixture. So we know our formula tells us the total is equal to the sum of the 3 components. So in that case, we write down our formula. And there it is right there. The total pressure is equal to the sum of the pressure of neon, argon, and xenon in this container. Now we need to make sure that all of those pressures that we're talking about are in the same units. I have 2 of them in atmospheres currently and only 1 in torr, so it makes sense to just convert that torr into atmospheres. So I have 1,525 torr, and I'm going to convert that by using my pressure conversion chart. So torrs is on the left middle side, atmospheres is right here. So I have 760 torrs equal to 1 atmosphere of pressure. Torrs is going to be on the bottom, and atmospheres is going to be on the top. When you put that in your calculator, you end up with 2.007 atmospheres of pressure. And that's our total pressure that we were just solving for there. And according to our equation, we now have everything in the right units, so we can just plug everything into our equation. So my total pressure, which is right here, is equal to the pressure of neon, which was given to us in the problem as 1.21 atmospheres, plus the pressure of argon, which was given to us as 0.20 atmospheres, plus the pressure of our gas that we're solving for, which is xenon. At this point, you literally just plugging it in and solving for X essentially, which is the pressure of xenon. So when I rearrange this equation, I'm going to subtract 1.21 atmospheres from both sides. And I'm also going to subtract 0.20 atmospheres from both sides to isolate that pressure of xenon. And when you do that math out, you end up with 0.0597 atmospheres is equal to that pressure of xenon. When you're using your significant digits, you would round this to 0.60 atmospheres. We'll do one more of these. So this one, we have a flask that has hydrogen and oxygen gas in it. Total pressure in the container is 1.03 atmospheres, and the pressure exerted by just the hydrogen is 395 millimeters of mercury. And it asks us what the pressure of the oxygen gas is. So again, first thing we want to do is we want to write down that equation, knowing pressure total is the sum of the pressure of, in this case, the hydrogen and the oxygen gas. So we'll write down that formula. And there's our formula right there. Total pressure is equal to the pressure of hydrogen plus the pressure of oxygen. Now we want to make sure that everything is in the same units. And since it asks us to report our answer in kilopascals, it makes sense to convert both those units to kilopascals now rather than waiting until the end, because we're going to have to do a conversion anyway. Our units don't match. I have millimeters of mercury and I have atmospheres here. So the first thing I'll do is I'll convert the first one, which is the 1.03 atmospheres, and I need to convert that into kilopascals. So again, using that chart, and there's our chart right there. We're going to go ahead and find atmospheres down this end, and then kilopascals down this end. And now we can do that conversion of 1.03 atmospheres to kilopascals. So if I have 1.03 atmospheres, I'm going to cancel atmospheres by writing that on the bottom, and kilopascals is going to go on the top. Move this over a little bit because I'm going to need more room there. 1 atmosphere goes on the bottom, and 101.325 kilopascals goes on top. Now you plug this into your calculator, your atmospheres cancel out, you're left in kilopascals, and you end up with 104.365 kilopascals, which with significant digits becomes 104 kilopascals. Now we're going to convert the next one. So our next one was given to us in millimeters of mercury. So we need to go ahead and use that chart again and find millimeters of mercury in kilopascals. Millimeters of mercury is over here. Kilopascals, same place over here. So I'm going to do 760 millimeters of mercury is the same thing as 101.325 kilopascals. So we're starting with 395 millimeters of mercury. And we're going to convert that by putting millimeters of mercury on the bottom and kilopascals on the top. So I have 760 millimeters of mercury and 101.325 kilopascals. You plug that into your calculator and you wind up with 52.662 kilopascals, which with significant digits rounds to 52.7 kilopascals. At this point, we have all of our information, so we can go ahead and plug it into our equation and solve. So our total pressure, which we saw for here, is 104 kilopascals. And according to our equation, total pressure is going to be equal to the pressure of the H2 plus the pressure of the O2, right here. So the pressure of the H2 that we just solved for was 52.7 kilopascals. And from that, we're adding the pressure of the O2. So the total of those two is going to equal 104 kilopascals. So now you just solve for the pressure of the O2 by subtracting 52.7 from both sides. And when you do that, you end up with the pressure of O2 being equal to 51.3 kilopascals, which if you're using appropriate significant digits, comes out to 51 kilopascals. So those are two examples involving just Dalton's law of partial pressure. So everything that's in the container should add up to the total amount of pressure that's in the container. Pay attention to your units, and it should be a pretty simple problem. The next thing we'll talk about here is mole fraction. So Dalton's law of partial pressures also comes with something called the mole fraction. And what the mole fraction is essentially is it's a ratio of how many moles of gas there are of one particular gas when compared to the moles of gas in the entire container. And you can use this because if you know the pressure of the entire container, you can multiply it by the mole fraction in order to figure out what the partial pressure caused by that specific gas would be. So for example, if we had two gases, gas A and gas B, in a container, I could find out the mole fraction of gas A by saying how many moles of A are there out of the total of A and B combined. And then I can multiply this by the total amount of pressure in the container. And by doing that, that tells me how much pressure just my gas A is exerting on the container. And you would do the same thing for gas B if you wanted to solve that way. So a couple of example problems we can do with this. This one here has us calculating the mole fraction of each gas that was found to be exhaled by someone using the data below. First thing we need to do is find the total amount of moles so that we can have that total to divide everything by. So we would add up all of these here to find the total. So when you put all those into the calculator and add them all together, you end up with 29.6 29.42 moles. So that's my total now. So we're going to go ahead and divide everything by that value that I just copied. So when we go ahead and divide each of these by the total of 29.42, just plug them into your calculator, and the answers you're going to get are as follows. Now you'll notice that none of your answers here actually have a unit, and that's because this is a unitless quantity. We're just trying to figure out basically a percentage, but we're writing it as a decimal to see what percentage of this container is made up of each of these individual gases. So the mole fractions are right there for you. So the first one is our mole fraction of N2, and it ended up calculating out to be 0.7056. Mole fraction of O2, the next one, 0.164. And you can read through them there. That's all of our mole fractions. So we'll go ahead and we'll do the next problem, which incorporates mole fractions with our partial pressures. So for this one here, we're told that our mixture of gases has 4.46 moles of neon and 2.15 moles of xenon. And we want to know what the partial pressure of each of the gases is, knowing that the total pressure is 2 atmospheres. So first thing I need to do is I need to figure out the mole fraction for each of these gases so that I can multiply it by that total pressure to figure out what the partial pressure would be. So I'm going to go ahead and figure out the total amount of moles of my gases. So I have 4.46 moles of neon, and I'm adding my 2.15 moles of my xenon in order to get the total amount of moles in the container, which comes out to 6.61 moles. So now that I have that total amount, I can divide each of those by the total amount to figure out what the what the mole fraction is for each of these. So I have 4.46 moles divided by the 6.61 total moles. When you put that into your calculator, you end up with 0.675 is your mole fraction. And then we have 2.15 moles divided by 6.61 moles. And you put that in your calculator and you get 0.325 is your mole fraction. So this is going to be my mole fraction for my first gas, which was neon. And this is my mole fraction for my second gas, which was xenon. So now when we're trying to figure out what the partial pressure of something is, the partial pressure of any gas, so the partial pressure of neon, for example, is going to be equal to the mole fraction of neon times the total pressure. And the total pressure was given to us in the problem as 2 atmospheres, and I just solved for the partial pressure over here of neon. So I have 0.675 times the total pressure, which was given to me as 2 atmospheres. When you plug that into a calculator and solve, you end up with 1.35 atmospheres. So what this tells us is the pressure that's being caused in this container by the neon is 1.35 atmospheres out of the 2 atmospheres total that are in the container. And you do the exact same thing for the pressure of xenon, which is going to be equal to the mole fraction of xenon times the total pressure in the entire container. And we solved that one to be equal to 0.325. So 0.325 times, again, that same total pressure of the container of 2 atmospheres. And when you solve that, you end up with 0.650 atmospheres. And when you're done with one of these kind of problems where you're trying to solve what the partial pressures are, if you add up your 2 answers, they should be equal to that total pressure of 2 atmospheres, which these are, so you know that you did your work correctly. So that's it for our mole fractions. We're going to do one more set of problems here, and that's when we're talking about collection of gas over water. So when you're collecting gas over water, there's one more thing you have to consider, and that's the fact that everything has a vapor pressure when it's in its liquid state. What vapor pressure means is whenever there is a liquid that has a surface that is in contact with air, some of those liquid particles are escaping the surface and turning into their vapor phase, or they're turning into a gas. Not a lot, but there is enough that it does cause some amount of pressure. And that pressure needs to be considered if you're collecting gas in a container, because not all of the gas that you've collected is going to be due to just that gas. It will also be due to those particles that are escaping the surface of that water. When you're doing these kind of experiments, you need to make sure that the gas doesn't react with water or dissolve in water, because then obviously your data will be incorrect. And the way that we would run this kind of experiment, you'd have an apparatus set up sort of like this. And if you look on the right, there's actually a diagram explaining what I've been talking about. So over here, the gas that you're collecting are the small blue ones, which are representing H2, hydrogen gas. But there are also a small amount of water particles floating around too. So the ones that have the red here. And those are just water particles that are slowly escaping the surface of this water right here. And they're coming up into the air around it, and they're causing a small amount of the total pressure that's inside of that container. So because of this, we know that the total pressure inside of that container where we've collected our hydrogen gas is going to be equal to the pressure of the hydrogen plus the pressure of the water. And therefore, if we wanted to know just how much pressure was caused by the gas that we created, so you create a gas over here, that gas comes into this container and flows up into this container that's full of water. And because gas is less dense than water, the air bubbles rise and you end up with some amount of gas inside of the container. So we know that the total pressure of that gas is going to be the sum of the water plus the pressure of the gas we put into the container. So we would just subtract the pressure of the water if we wanted to know what the pressure of just the gas we created was. So if you look here, this reference sheet is also provided to you on Schoology in your references folder. This tells you what the vapor pressure of water is at any of these given temperatures. So whenever you see one of these problems, one of the things it has to tell you is what the temperature of the water is, so that you can know how much pressure is being caused by the vapor of coming out of the water. And this will always be in that folder for you, so you guys can use it as a reference. And notice the units are given to you in torr. So where necessary, make sure you do that unit conversion. So here is another example of an apparatus. So what happens is you have a sample here. This is decomposing. So we're decomposing a sample here, and that sample is producing gas. The gas travels up the tube, and then it goes through this tube and into this container, which started out as full of water. And those bubbles slowly float up to the surface, and then they fill the container up here with oxygen gas. And as it fills the container, it pushes some of the water out. This water level rises in response, and this water level decreases, and it keeps going down. So here, as we're collecting the gas, we can figure out the total pressure caused by just that gas by doing that subtraction. Another important thing to note here is when we find that point where the water level is equal, so the water inside this container is equal to the water that's outside of the container, that means the pressure inside the bottle is equal to the pressure that's outside of the bottle at that point. So total pressure is equal to pressure of the gas plus the pressure of the H2O. We're going to do a couple of examples here, and then that'll be it, and you guys can go ahead and start your homework. This first one here says oxygen gas from the decomposition of our potassium chlorate was collected by water displacement. The barometric pressure and temperature were 731 torr and 20 degrees respectively. What's the pressure caused by just the oxygen gas? So the information that it gave us here is 731 torr. This is going to be our total pressure. And it gives us a temperature here. This temperature, remember, we can look up on that graph that chart that I just showed you to see what the pressure is for any water vapor. So first we need to look for 20 degrees Celsius. 20 degrees Celsius is right here. And it tells me my pressure is going to be 17.535. And that's again measured in torr. So I have 17.535 torr. So 17.535 torr of pressure created by just the water. So this is the P H2O. So now I know my entire formula is that the total pressure is equal to the pressure of the water plus the pressure of the gas. So there's my equation. I can go ahead and rearrange that equation just by subtracting the pressure of the water from both sides. And when I do that, it tells me that the pressure of O2 is equal to the total pressure minus the pressure of the H2O. So at this point, I have all of my information. I have my total pressure here, over here, and then I have the pressure of my H2O right over here. So I can just plug these in and solve. So total pressure was 731 torr minus the pressure of the H2O, which we looked up on that chart to be 17.535 torr. When you plug that into a calculator and solve, you get 713.47 torr, which if you're using significant digits, rounds to 713.5 torr. So we have one more example problem we'll go ahead and do. This last problem that we're going to go over is just another one of collection over water, and it tells us that our O2 is collected over water on a day where the atmospheric pressure is 762 torr. So this right here is telling me the total pressure of the environment that day. So my total pressure is 762 torr. It tells me the temperature was 23 degrees Celsius. So now that I have my temperature, I can go ahead and refer back up to my chart here. 23 degrees Celsius is 21.068 torr. So the pressure of my water, 21.068. And it asks for the pressure of the dry oxygen gas. And by dry oxygen gas, it means remove the pressure that's being caused by the water, which is not dry. So the pressure of the dry oxygen gas is going to be the total pressure minus the pressure of water. So there's our formula right there. We just need to plug our numbers in now. So the total pressure we solved to be 762 torr minus the pressure of water, which we found on our chart to be 21.068 torr. Now when you plug that into your calculator and you solve, you wind up with 740.932 torr, which if you're using appropriate significant digits, comes out to 741 torr. So that's your final answer right there. So that's just another example problem on how to do these problems when you're talking about collection over water. At this point, you guys are ready to start your practice, so you can go ahead and download that Dalton's Law worksheet off of Schoology. Just so you're aware, there's another resource on Schoology for you in that references folder. Here, this gives you all the information on things that we've covered already and a couple things we haven't yet that you'll see in future weeks. So it has all of our temperature conversions here, our pressure conversions, your empirical gas laws, everything that we just talked about this week. So the combined gas law and Dalton's partial pressures are on the left here. On the right is stuff we'll get into next week. And then a little bit more information down at the bottom, just general constants and things like that that we'll get into. So go ahead and start your practice.